that too much or is that okay? Good evening, Altrincham. Pleasure to be back again and talk to you once more. This one, as you can see, self-evident. I'm talking about nothing smaller than the beginning of everything. The origin, and in particular, the very early history of the universe in which we live. When we look out into the universe, we see an awful lot of stuff. And the question I'm trying to answer this evening is, where did all that stuff come from? Where did all this hydrogen and helium and dust and gas and stars and galaxies arise? Now, when we look out into the universe, this looks like a sort of CGI pretend universe, but in fact this is more like a 3D atlas. In other words, lots of galaxies have been mapped in terms of their position on the sky and how far away they are, which you can then generate a 3D atlas, and this is effectively a fly-through of that 3D atlas. So this is all genuine data. We notice that the universe, especially the universe fairly close to us, seems to be chock full of galaxies. But those galaxies aren't randomly distributed, they're not uniformly distributed, they appear to occur in clusters. Every once in a while we see a whole knot of galaxies existing in the same place. Occasionally we see filaments, lines of galaxies. And every once in a while we see a little part of our local universe which appears to be almost devoid of galaxies. So the universe in which we live is by no means uniform. It's structured a particular way. But as much as anything, rather than talking in detail about why they have these particular positions, we're really just trying to work out why there is anything there in the first place. We know in the observable universe, we think we can calculate in the observable universe, which appears to be a sphere, about 100 billion light years across or thereabouts. Within that sphere, there appears to be 1 trillion galaxies. Each of these galaxies have probably got hundreds of billions of stars. Stars and gas and dust, all this hydrogen, all this helium, all these other gases, all the stuff that makes us, where did all that stuff come from in the first place? Now we can take a snapshot of the universe, such as, for instance, a Hubble Deep Field, and we see some galaxies quite close and some galaxies quite far. This is a slightly different scale to the previous one. The previous fly-through was a lot of galaxies, maybe 1 million galaxies or so, fairly close to us. In a Hubble Deep Field, we're looking much further, much deeper into the distance and hence into the past. But still we have the basic fundamental question that we see thousands of galaxies and we deduce that each of these galaxies has got many, many stars in them. What is it that produced all of this stuff? Where did this stuff come from? So I'm talking about the creation of the universe, which as far as we know, to the best of our knowledge, happened about 13.8 billion years ago. How long did it take to make the universe in which we live? About 3 minutes, and I'll say why it is that we come to the conclusion it took 3 minutes to make the universe in due course. A question that's often asked is, where did this Big Bang happen? And the answer is it happened everywhere, because the Big Bang was the start of everything. It was the beginning of everything. Every point in the universe that you can think about was made at the same time in a Big Bang, and therefore it didn't happen at one particular point in space. We can't point to a point in space and say that's where it happened, because every point in space was generated 13.8 billion years ago. Why did it evolve the way it did? If it was born 13.8 billion years ago, why did we end up with a universe that looks the way it does now? Well, that's because of the laws of physics. And how do we know all of this? Same answer, because of the laws of physics. So that's really what I'm going to be talking about this evening. How do we work out what the laws of physics are that get us from the origin of the universe to where we are today? You can think of it as an analogy by asking, well, instead of asking how did the universe get born and end up the way it is, what are the rules of physics, what are the laws of physics that dictate how the universe came to look the way it does, we could ask ourselves a parallel question and say, if we were trying to work out not the laws of physics, but the different rules of the game, not the rules of the game for the universe, but the rules of game for this thing, chess. Could you work it out from a picture like that? If we showed somebody who's never encountered chess, here's a picture of a game, can you work out what the rules of the game are? We come to the conclusion, no, it's rather tricky. We might come to the conclusion that there are some gold pieces and some silver pieces, so presumably it's a game of two players. But why is it on a checkerboard? Why are they positioned the way they are? Why is one of them fallen over? You can't work out the rules of the game just by looking at a snapshot. And similarly, you can take a snapshot of the universe, you can take a snapshot of a galaxy, and you can ask the question, well, can we work out how that galaxy ended up looking like that from a static picture of the galaxy? And the answer is no, for essentially the same reason. We don't have enough information. We are fairly sure that galaxies rotate, but we haven't got the patience to sit and watch it rotate. It would take a few 100 million years for it to rotate once. So we can't sit down and watch the galaxy rotate. If we don't have the same option here, it would be great if we could just watch a video of the chess game being played, because if we watched the chess game being played, we would have a clue of what the rules of the game are. We'd see how pieces move, etc. We would realize that one player moves and then the other player moves, and each of these pieces has a particular meaning. Its shape determines how it can move across the board. But just like we can't, with a galaxy, basically watch it in motion, we haven't got the patience to sit and watch that evolve. For the same reason, we haven't got the patience to watch a chess game in motion. But what's the alternative? Well, instead of watching a video of a chess game, what we could do is not photograph one chess game, we could photograph 1 million chess games, all in process. Even if we can't watch them evolve, if we had 1 million snapshots of 1 million chess games, just like in principle, we can take 1 million snapshots of 1 million galaxies, then we would have a chance, even though we can't watch each of them change, if we've got a number of different galaxies imaged, and remember these are at different distances, so because of the finite speed of light, effectively we have them at different times as well. It's like taking a snapshot of the game in progress at different times during the game. So if we have enough data from images like this, then we stand a chance of working out what the rules of the game are that determine how these things came to be the way they are. Of course, these days, perhaps we ought to replace the Hubble Deep Field with the equivalent of a James Webb Deep Field, but it's basically the same information. The James Webb might be able to go a little bit further back in time, but we still have the same problem. Why do we end up with a universe that looks like this? And where did all this matter, all of these stars that are shining back at us, all of these trillions of stars, where did they come from in the first place? You might say that this is far too complex a question. How can we possibly answer the question, where did all of this stuff come from? We look just at our local bit of the universe, just a little bit of the Milky Way, and it looks incredibly complex. Surely the rules that determine that we end up in a universe that looks like this are far too complex for us to figure out what the rules are if we end up with something as complex, even if as beautiful as this. But just because something is extremely complicated doesn't mean the rules that determine how it came into existence are complicated. In much the same way that you can take a mathematical set of points, this happens to be the Mandelbrot set, it's a fractal set, and each pixel on the screen is a particular color which has been determined by a mathematical formula. This is only a tiny snapshot of the Mandelbrot set. It's, I don't know, maybe 1 million pixels or something like that. But in principle, we could zoom in as much as we like, and we could zoom in to give you a part of an image that would be 1 billion pixels, or 1 trillion pixels, or 1 quadrillion pixels. In principle, there's no limit to how much you can zoom in. You might look at this and say, yeah, but it's the same pattern repeating over and over again because I can see a particular motif here which keeps cropping up. Well, it's similar. Yes, this motif here is similar to the one next door, which is similar to the one next door, but they're not actually the same. In much the same way that one of the 100 billion stars in our galaxy might look similar to another star, but it's different. So, if this is an analogy to the universe containing quadrillions of pixels, each with their own color, and this pattern never repeats and is arguably infinitely complex, How complicated is the formula that allowed us to generate each and every pixel, not just the ones we're looking at, the entire set of pixels of the Mandelbrot set? Well, the rules of the game for this is that z equals z squared plus c. I'm not going to talk about the maths of why that's the rule, but that's it. An incredibly simple formula gives us an incredibly complex result. So just because we look at the universe and say, wow, it's really complicated, doesn't mean the rules of the game aren't fathomable. It's not necessarily the case that we can't figure it out. One of my favorite quotes of Einstein is, the most incomprehensible thing about the world, or universe if you prefer, is that it is comprehensible. Remember, we're just monkeys who came out of the trees a few million years ago, walked around on our hind legs, and ever since we've been evolving, and somehow we've managed to evolve into a species which is capable of comprehending how the universe is put together. There's no particular reason why that should be the case. The universe doesn't owe us anything, and yet we are now able to think about the universe and our place in it, and are able to figure out what the rules of the game must be such that we exist. So, what's the train of thought, if you like, the flow of thought that allows us to get to the place where we want to be, where we start asking the question and answering the question of how do we end up with a universe like this one? So, an observation from about a century or so ago, galaxies are all moving away from each other. And so we come to the conclusion that the universe is expanding. The first one is simply an observational fact. The second one is an inference from the observation. If the galaxies are all moving away from each other, it looks like the universe is expanding. Another observation, or set of observations we can make, is the fact that we can do experiments. We can do physics experiments here on Earth and try and figure out how things are put together. For instance, we can bang protons together in a particle physics experiment, such as the Large Hadron Collider, and we can get an idea of what we're made of. We're made of molecules, molecules are made of atoms, atoms are made of smaller stuff, etc. And we can make a few assumptions about if we can do the physics here on Earth to understand how stuff is put together, and we can make observations about the universe, we have to make some assumptions about how those two things are linked. We have to make, if we want to make progress, we have to make the assumption that the laws of physics in one place are the same as the laws of physics in another place. If the laws of physics as determined in Liverpool were not the same as the laws of physics as determined in Timperley, then we are on a hiding to nothing. We will not make any progress if the laws of physics are different for everybody. Unless we can reproduce an experiment here in England and assume that the same experiment done in Australia will give us the same results, and the same experiment done in Alpha Centauri or the Andromeda Galaxy or the other side of the observable universe, we assume that the laws of physics are the same everywhere, because otherwise, how can we possibly make sense of anything? The same is also true of the second assumption. We have to assume that the laws of physics now are the same as the laws of physics as they were in the past and as they will be in the future. Same assumption, effectively. If we say, well, maybe the laws of physics we determine here and now today will be different tomorrow, then we can't, again, possibly make any headway in understanding the universe, because by definition we're looking at the universe as it was either seconds ago or years ago or millions of years ago or billions of years ago. If the laws of physics have changed, then we haven't got any chance of understanding what is out there. So we have to make those assumptions, otherwise we can't make any progress at all. But if we assume that's the case, we assume that we understand how the world is put together here on Earth, we assume the laws of physics are the same everywhere, and we apparently live in an expanding universe, we come to the conclusion that the universe was created in a very hot, dense state 13.8 billion years ago. That's derived from the evidence that we have, and it's been expanding and cooling ever since. And the question we're addressing is, okay, we see a lot of matter out there. We see a lot of gas and dust and stars and galaxies. Where did all that stuff come from? Can we work out the rules of the game and figure out the question? If the universe is 13.8 billion years old, how far back in time can we go before we think, well, I'm really not convinced that the laws of physics as we understand them still apply when we go back to a certain point in time. In other words, how far back can we go before we give up and say we really don't know what's going on? If the universe is 13.8 billion years old, can we go back to the first year of that 13.8 billion year history? Yep, no problem at all. Can we go back to the first day? Okay, the Earth doesn't have a day back in, but you know what I mean by the time. Yeah, we can go back to the first 24 hours of the universe and still believe that, yep, the physics we understand at that point. Can we go back to the first hour? Yes. What about the first minute? Yes. What about the first second? Yes. What about the first millisecond? Yes. What about the first microsecond?
Yes.
Yes. What about the first nanosecond? Yes. What about the first picosecond? Not really, no. 1 picosecond is about the limit. 1 picosecond is 1/1,000,000th of a second. Before that, when we go backwards in time, we really don't claim to understand what was going on during that first picosecond, during that first 1/1,000,000th of a second. Before the first picosecond, we are on absolutely shaky ground. No physicist will claim that they really have any evidence that they know what was going on during that time period. After that first picosecond, after that first 1/1,000,000th of a second, from that point onwards to the present day and beyond, we think we're on relatively solid ground, relatively well understood. Okay, relative is a relative word. That doesn't mean we understand everything. There are still various mysteries to be solved. But in terms of the grand picture of understanding the rules of the game, everything from 1 picosecond onwards, we think we have good reason to believe that we understand. And I'm going to tell you in a little while why we have that watershed at 1 picosecond. Before a picosecond, not sure. After a picosecond, we are on pretty solid ground. So that was a rather lengthy introduction to what it is I'm talking about this evening. Before we launch into let's have a look at what happened when, I'm going to put up a slide with a few basic ideas. Some of those ideas you'll be familiar with, some of those ideas maybe not, but we'll make sure that we're all on the same page, if we excuse the cliche, before moving on to ask what happened in the first fraction of a second, what happened in the first few seconds, what happened in the first few minutes. We're not going to go at that same speed for the rest of the evening, otherwise it'll take a while. We'll then change gear and jump fast forward to what happened in the next 380,000 years. Again, that time is not arbitrary. There's a specific reason for jumping to 380,000 years after the Big Bang. And then again, we'll change gear a second time and then just whip straight to the present, 13.8 billion years, just to get up to where we are now. So that's what we're going to do in the next 3 or 4 hours, whatever. I'm not sure how long I've got. I'm not going by that clock because that seems to be wrong, so we'll forget that. So first off, let's make sure that we understand a few basic ideas before we start asking really deep questions like what was happening in the universe. Firstly, I hope everybody is happy with that statement. We are made of atoms. Okay, an atom is a nucleus of positively charged particles. They happen to be protons and neutrons. Those are just the labels we give to these particular particles. And we've got a whole load of negatively charged electrons buzzing around. That's how we tend to think of atoms. Not a particularly great picture, but it'll do for what we want to understand of what's coming next. Now, atoms, as I've just said, positively charged nucleus, negatively charged electrons. So atoms are not fundamental. They are made of smaller bits. They are made of smaller stuff. We found that out quite a long time ago, many, many decades ago, more than a century ago. When it comes to, okay, an atom is made of smaller stuff, what about that smaller stuff? Can we keep on subdividing? In other words, an electron, to the best of our knowledge, an electron is not made of anything. You can't take an electron and say, let's cut it in half and have a look inside and see what it's made of. As far as we know, electrons aren't made of anything. They are just electrons. Whereas a nucleus, the nucleus of an atom, is either, one way of looking at it, you either say it's not a fundamental particle, meaning it's got structure, or you say it's a compound particle, which is the same thing effectively. It is made of something else. And we found out, again, a century or so ago, that if you use enough energy, you can take the nucleus of an atom and you can split it. You can change it, you can look inside it, and you find that a nucleus is actually made of two particles which we call protons and neutrons. It doesn't really matter, but protons are positively charged and neutrons are neutrally charged. That doesn't matter too much for what we're talking. The point is the nucleus is made of other stuff. Are protons and neutrons fundamental? No. You can take a proton and ask the question, what's inside a proton? And it turns out protons and neutrons are made of smaller things with rather silly names, quarks. So it doesn't, again, matter why we're giving them these particular labels. We're not going to worry about why we call them quarks. All that matters is protons are made of smaller things. Those smaller things are called quarks. Just so happens there's 3 of them that make up a proton. The same is true of neutrons. I'm just using the proton as an example. So what we have is a sort of Russian doll model. We know that we're made of molecules. We know molecules are made of atoms. Atoms are made of nuclei and electrons. Nuclei are made of protons and neutrons. Protons are made of quarks. And as far as we know, quarks aren't made of anything. Like electrons, as far as we know, you can't take a quark, cut it in half and look inside. It doesn't look like there's anything in there. They appear to be fundamental particles. But it takes a certain amount of energy to separate a molecule into atoms. It takes more energy to separate an atom into its constituent parts. It takes even more energy to break a nucleus apart into protons and neutrons. And it takes even more energy to look inside protons and neutrons and find out what they're made of. So there's an implicit energy scale from low energy to high energy in this Russian doll idea of how the universe is put together in terms of matter that we can study either here in the laboratory or elsewhere. Remember, we said the deduction is the universe was born in a very compact, hot, dense state and has been expanding and cooling ever since. So low energy is up there, high energy is down here, and to a physicist, low energy effectively means low temperature. Temperature is just a way of measuring how much energy each particle has. So low energy is effectively low temperature, high energy is high temperature. So if the universe was born hot and is cooling down, then there's an implicit timeline running up this scale. And what we can interpret that as meaning is that in the early days, the universe was so hot, there was no way that, for instance, quarks could get together to make a proton because they had so much energy, there's no way those quarks would stick together to make a proton. You have to wait until the universe is cold enough that it doesn't have so much energy that protons can't exist. And similarly, when you want protons and neutrons to make a nucleus, you have to wait until the universe is cooled enough, because if you try and put protons and neutrons together to make a nucleus, if the universe is too hot, if you try and do this too early, they'll have so much energy they'll just shake themselves apart and you won't make a nucleus. So you make things from the bottom up. As the universe cools from a hot state to a cool state, as it expands and cools, you can make protons, then you can make nuclei, then you can make atoms, then you can make molecules, then you can make us. That's the order in which the universe was built. That's how we understand the basic rules of the game, by thinking about the energy and the temperatures involved. So let's get the most difficult question out of the way early. What happened at time t equals 0? But remember, this is the time before the first picosecond. So the answer is, well, we don't really know. Science cannot provide a definitive answer of what happened at the instant of t equals 0, because it's earlier than we have any experimental evidence to back us up. You can come up with any conjecture you like, you can come up with any hypothesis you like, but remember, a hypothesis in science is only useful if it's testable, and at the moment we can't test any hypothesis of what happened at time t equals 0. It is widely thought by people who have studied quantum mechanics. Quantum mechanics is the theory of what happens on a very small scale, and presumably in the very early universe it was a very small scale, so presumably quantum mechanics applies. Quantum theory tells us that it is actually possible to borrow energy from nothing, a so-called quantum fluctuation. That sounds really weird, but quantum theory is really weird. Quantum theory has been with us for 100 years, and we have not yet proven it to be incorrect in any way whatsoever. So if we know that quantum theory allows this, then maybe that's what happened at the time t equals 0, a quantum fluctuation. Energy was borrowed from nothing. And yes, it sounds weird, but that's the topic of a completely different talk on the weird world of the very, very small. How much energy can you borrow from the bank of nothing, as it were? Well, there's a limit to how much you can borrow and for how long. Pretty much the same as if you want to borrow money from a bank. If you borrow a lot of money for a short time, you get a certain amount of interest. Alternatively, you could borrow a small amount of money for a longer time and still pay the same interest. What you can't do is borrow a huge amount of money for a very long time and expect not to pay any interest back to the bank. So just like that, quantum theory tells us that the amount of energy you borrow from nothing has a time limit. And when you multiply the two together, that gives you the limit, the amount of energy multiplied by the time you've borrowed it. So a lot of energy for a short time or vice versa is perfectly okay according to our understanding of quantum theory. But if you work out the amount of energy you have to borrow, what is the total energy of the universe? People have tried to measure this, and the answer seems to be about 0. Because if you work out the total amount of mass in the universe, you get a particular answer. You work out the total gravitational energy in the universe, you get a similar number but negative, and when you add them together, the answer seems to be somewhere around 0. We can't pin it down exactly, but some people believe, well, maybe the total energy of the universe is absolutely 0 rather than just approximately 0. And if it is 0, then you've got as long as you like to pay back the loan. Now that sounds like a cheat, I'm sure. But then there's an awful lot in quantum theory that sounds like a cheat. That's why it takes quite a few years to teach it to undergraduates how quantum theory works. So this is speculation. This is a possibility. It's not an answer. It's a possibility, and we have not been able to verify this because we do not have the experimental evidence that will prove this is what actually happened. But a number of people think that this is consistent with our understanding of quantum theory. Let's move forward a long time into the future. We've now gone from t equals 0 to this particular point, 0.0000 seconds. Okay? So we've gone forward to the point where the universe has expanded from essentially a point until it's now approximately the size of a golf ball. And by the universe, I mean our observable universe. We don't know what's going on outside our observable universe. So what I'm saying is everything that is currently inside our observable universe, inside this sphere, 100 billion light years in diameter, everything that's inside that sphere used to be a lot closer together. And at this point in time, everything in that sphere used to be just a few centimeters apart. So it's rather difficult to visualize and imagine getting the entire observable universe into something the size of a golf ball, but that is, we believe, the state of the universe as of 10 to the minus 35 seconds after its creation. I like this particular analogy because not only does it make us think of how close together everything was in the very early universe, it also reminds us that the universe had dimples. Now, okay, not dimples in the sense of a golf ball, which has got small physical dimples in the surface, but the early universe did have dimples in the sense that it wasn't perfectly uniform. It had variations in density, variations in temperature. This is typically what you get for a random fluctuation, and when you borrow energy from nothing, you don't assume that what you end up with is a perfectly uniform sphere. It will be small variations. We don't have to worry about how big. There are small variations in density of temperature of the energy that you've borrowed from the vacuum, from nothing effectively. Now eventually, when the universe has expanded to a much, 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 much bigger sphere, those dimples will give rise, because we've got variations in density and variations in temperature, ultimately these are going to give rise to the variations in density that we see around us. The fact that some regions have galaxies and some regions don't have galaxies is a consequence of the dimples that existed in the golf ball. In other words, this small variation here will ultimately give rise to the large-scale formation of structures in the universe. So we've moved forward from 10 to the minus 35 seconds to something in which we are now on much, much, much steadier ground. We've now moved 1 picosecond after the instant of t equals 0. And at this particular point, 10 to the minus 12 seconds after its creation, the universe has expanded from essentially nothing, or golf ball size, to something about the size of the solar system. Yes, of course, the solar system doesn't exist yet, but just to give you an idea of scale. It's gone from something effectively zero size, almost zero size, to something a few light hours in diameter, but it's only taken 10 to the minus 12 seconds to do that. So clearly the expansion of the universe has taken place much, 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 much faster than the speed of light. It's gone from nothing to light hours, but it didn't take hours to get there. It only took this tiny fraction of a second. So the universe at this point was expanding far faster than the speed of light. The temperature at this point has fallen to a fairly balmy 10 to the power 15 Kelvin. And we think that the constituents of what was in the universe at this point, well, we can't be definitive, but we think if you borrow energy, that energy can be used to make almost anything you like. E equals mc squared. You can make as much matter and antimatter as you like if you've borrowed some energy. The reason we think this first picosecond is important in terms of our understanding is from this point onwards, the energies involved, either the temperature or the energy, whichever way you prefer to think of it, is comparable to what we can reproduce in the Large Hadron Collider. In other words, when we bang protons together at the maximum energy of the Large Hadron Collider, we've got individual particles whose energies are comparable to the energies that particles would have at this particular point thereafter the Big Bang. And hence, if we want to test something, if we think something happened at this point, we can test it by generating the same energies in the Large Hadron Collider. So this is, remember, the basic tenet of science. If you've got a hypothesis, you come up with a theory, you test it by doing experiments, and you see if you're right or you're wrong. And from this point onwards, we can do that because we have access to these sorts of energies hereafter. Because we can test our ideas, from this point onwards, we've got a reasonably good idea of what happened. Up to this point, speculation. From this point onwards has been tested over and over and over again by experiments, by simulations, by tests to see have we got it right. And so far, the Big Bang theory seems to be the best theory to explain how this all happened. What happened to matter and antimatter? Well, we borrowed energy, and we can use that energy to make matter and antimatter. Energy and matter and antimatter are continually exchanging backwards and forwards. Originally, matter and antimatter are made in equal amounts. If you've got a certain amount of energy, if you want to make some matter, you've got to make an equal amount of antimatter. They always occur together. They are mirrors of each other in the sense of if you want to make an electron, you have to make an anti-electron. An anti-electron looks like an electron. It has the same mass, the same properties, except it has the opposite electric charge. That's what we mean by antimatter. It looks like every particle of matter has got a twin, if you like, a particle of antimatter. And when energy is used to make matter, it makes an equal amount of antimatter. I don't know how to express energy as a nice graphic, so I'm just using capital E as a certain chunk of energy. Energy can make a particle of matter and a particle of antimatter. It probably won't make a tangerine and an anti-tangerine. The point is it doesn't matter whether it makes a quark and an anti-quark, or an electron and an anti-electron, or particle X and anti-particle X. Energy will make stuff in huge quantities, and it will make matter and antimatter, and when matter and antimatter get close to each other, they will annihilate and generate energy. In other words, energy will make matter and antimatter, which will then get converted back into energy, back and forth and back and forth. Having converted energy into matter and antimatter and then back into energy, that same energy doesn't need to make the same two particles again. In the next tiny fraction of a second, it could make a completely different type of particle and antiparticle. Probably not a hot dog and an anti-hot dog. It doesn't matter. It's going to make something out of matter, and it must make an equivalent something out of antimatter. Back and forth and back and forth. Stuff to energy to stuff to energy to stuff to energy. and it will be making quarks and electrons and all sorts of other things. I'm just going to assume that there's lots of particles floating around, and I'm just going to call it a quark soup, because I don't want to keep calling it a soup of quarks and antiquarks and electrons and anti-electrons. So quark soup is just a shorthand for all of this stuff. But here's one of the mysteries which we haven't solved yet. Somehow, at about this time, around about this time, for some reason or another, the balance that we think should always be there between matter and antimatter, somehow that got out of balance. For some reason, nature decided to make more matter than antimatter. And we don't understand why. We can measure that imbalance now. We can characterize it in the laboratory, but we don't understand why it chose to do that at this particular point and why it chose this particular imbalance. Here I'm representing the imbalance by saying there's more matter than antimatter, there's more tangerines than anti-tangerines. And I've shown a 10% imbalance, as if there's 10% more matter than antimatter. In fact, the imbalance wasn't anything like that large. The imbalance was not 1 part in 10, the imbalance was 1 part in a billion. So there was only a tiny, tiny, tiny excess of matter over antimatter. But that tiny excess was important because each of these matter particles is going to annihilate with its antimatter equivalent, and so you're going to get a lot of annihilation, which will produce an awful lot of energy, which ultimately will end up as radiation. So think of this energy as either gamma rays or ultimately just light. Doesn't really matter what frequency of light, what wavelength of light, it's just radiation. So we can think of it simply as light. But of course, this one, because we have a slight excess, it's got nothing to annihilate with, which means we're left with a little bit of matter left over. So we should be in a universe, according to this theory, which is absolutely chock full of light. There should be loads of photons of light around and a tiny excess of matter. And that is indeed what we see in our universe. If we count how many particles there appear to be in the universe and how many photons of light do there appear to be, yes, light seems to outnumber particles by 1 billion to 1. So that seems to be a prediction that we can actually test. And of course, this tiny 1 part in 1 billion which is left over is everything that we see. It's all matter. It's every star in every galaxy in the observable universe, and it is the sun and the earth and us and everything else we see around us. So we're very grateful for the fact that matter and antimatter weren't made in equal quantities, because if they were, we'd end up in a universe which was full of light and there would be nothing else other than light rattling around in an otherwise empty universe. So we're very grateful for this slight imbalance, even if we don't understand exactly what its origin is. Let's move fast forward to 1 millisecond after the instant of creation. Matter and antimatter are continuing to pop into and out of existence. Matter and antimatter, energy, energy, matter and antimatter. Back and forth, back and forth. Eventually, because we're now at the point 1 millisecond later, the universe has cooled off enough that it's possible for those quarks to get together and make protons and neutrons. We're not going to turn this into a particle physics talk. All I'm worried about, all I care about, is the fact that certain quarks, when they get together, you can consider this bag of 3 quarks to be something that we would label, well, we call those bags of quarks a proton. And if you have a different arrangement of quarks, I'm not going to explain the difference between U and D, and I'm not going to explain why they're colored red, green, and blue, but a different combination of 3 quarks, if they were to get together, we call that particular grouping, that particular bag of quarks, we call that a neutron. Now, the universe is now cold enough for these 3 quarks to get together. Up to this point, the universe was so hot that any attempt at 3 quarks getting together, they were so energetic they would just basically not form a little trio. But now the universe is cold enough for a collection of quarks called protons to exist and a collection of quarks called neutrons to exist. It is still possible that quarks and antiquarks will annihilate to make energy, which makes quarks and antiquarks not necessarily the same ones again. So quarks can change, which means a neutron can change into a proton, and a proton can change into a neutron. The universe is certainly hot enough that they can still change backwards and forwards. So we would change the label depending on which particular quarks we've got in our bag of quarks. If we go to a first few seconds, and now we're talking about of order 1 second after the Big Bang, the universe has cooled off to only about 1 billion Kelvin. That still sounds ridiculously high, but remember the core of some stars is actually quite high, so this isn't such a silly number, this 1 billion Kelvin. It is now, even the 1 billion Kelvin sounds hot, it's actually too cold for protons and neutrons to readily swap backwards and forwards. In other words, that happened up to this point for the first few milliseconds. It was hot enough for quarks and antiquarks to change into energy and back and forth, but now they are sort of frozen in the sense that the universe isn't hot enough for that to happen. Now we know that protons are a little bit lighter than neutrons by about 0.1%. How do we know that? Because we can measure it in the lab here and now. And remember, the laws of physics we believe are immutable. So if protons are lighter than neutrons now, then protons were lighter than neutrons 13.8 billion years ago. And they will be 1 trillion years from now. That is a fundamental property of these particles. They can't just choose to be any mass they like. So if protons are a little lighter than neutrons, as indicated by this sort of scale, and hereafter I'm going to represent protons as red circles and neutrons by blue circles, what happens is, at this point, 1 second after the Big Bang, protons outnumber neutrons, and it turns out that they outnumber in the ratio of 3 to 1, 75 to 25. I've taken a representative set of 16 particles, so three quarters of them are protons, 1/4 are neutrons. Why should you make more protons than neutrons at this particular point? Because they're lighter. If they're lighter, they're easier to make. Nature will always take the easy way out. Nature always favors the lower energy, or in this case, the lower mass, because mass and energy are effectively interchangeable. So if you give nature the option, make as many protons as you like and make as many neutrons as you like, if protons are slightly lighter, it will make more of them. And the calculation from our understanding of nuclear physics and the properties of particles is such that when the universe was about 1 second or so old, it should have made 3/4 protons, 1/4 neutrons. That's not quite the final story because we know that neutrons are unstable. How do we know neutrons are unstable? Because we can measure that in the laboratory. Take a neutron on its own, separate it from all its friends, eventually it'll change into something else because neutrons are unstable, a bit like radioactive atoms are unstable. So on a time scale of now a few minutes, 100 or maybe more than 100 seconds, let's say 2 or 3 minutes scales, because neutrons are unstable, some of them will change from neutrons into protons. Some of those quarks will change internally, rearrange themselves, and we'll end up with some of those blue changing to red. So instead of having the ratio of 12 to 4, some of them will have changed. So 2 of those blues have now changed. So now we have 2, 4, 6, 7. Now we have 14 reds and 2 blues. So we have 14 protons and 2 neutrons in our little selection of 16 particles to illustrate what's going on. The next step is the key one in terms of giving us something that gives us predictability. Remember, the Big Bang theory is of no use unless it can make predictions which we can actually test. Once the universe has cooled to the point of 3 minutes or so, the universe will only be 100 million Kelvin. And at this point, the individual protons and neutrons that have been floating around in our soup of matter that's been made from the energy we borrowed from nothing, up to this point, the energy has been so high, the universe has been so hot, none of these protons and neutrons can ever get together and stick together. But from this point onwards, they can. The universe is now cold enough that protons and neutrons can get together. And one of the most stable structures that you can make in the universe is this one. 2 neutrons and 2 protons together give you a structure So 4 nucleons, as we call it, in other words, a nucleon is just the collective name for a proton or a neutron. When 4 of them get together and 2 neutrons stick to 2 protons, that is a very stable structure. Once it's made, it's very difficult to tear it apart. So when you've got a large collection of protons and neutrons, what's going to happen? 2 of the protons are going to pair up with 2 of the neutrons and make this very stable structure, which we either call an alpha particle or we call it the nucleus of a helium atom. Two labels for the same structure, 2 protons and 2 neutrons. But that leaves you with a whole load of bachelors, because once 2 neutrons have paired up with 2 protons, these protons do not have neutrons to pair up with. Because of the protons outnumbering the neutrons, you end up with, in this particular collection of 16, 1 nucleus of helium, and all the other bachelors are left as just protons floating around. A proton is simply the nucleus of a helium atom. So the prediction is that after 2 or 3 minutes, 3 minutes tops, you can't change that. The amount of hydrogen in the universe and the amount of helium in the universe is dictated by the state of the universe 3 minutes after it started. And that's a prediction of how we think protons are made and neutrons are made, and working out the physics of what would we expect in terms of how many of these particles are made, and our understanding of stable structures like the nucleus of helium. So the prediction is, when we look out into the universe, if Big Bang theory is correct, when we look at everything that's out there and we say how much hydrogen is out there and how much helium is out there, we should get the ratio by mass of 3/4 hydrogen, 1/4 helium. When we look at all the gas that's out there, what do we actually find? What's the observable evidence? The answer is 3/4 hydrogen, 1/4 helium. The Big Bang theory predicts that that must be the case. It can't possibly be half and half. It can't be 90% hydrogen and a little bit of helium. It must be 3/4, 1/4. And that is indeed what we see. Now you might say, well, surely that can't be right, because don't stars start with hydrogen and then make more helium? Well, they do, but amazingly enough, even though lots of stars have been changing hydrogen into helium, it hasn't actually changed the total amount of gas in the universe that much. In other words, despite the fact that there are billions of stars out there, that ratio is still roughly the same as it was 3 minutes after the universe was made. Stars haven't made that much of a dent in all of the hydrogen that's out there yet. They will eventually. Eventually stars will mop up all of that hydrogen. But the universe is only 13.8 billion years old. It's only a baby. It hasn't had time yet to really make inroads into all of that hydrogen. So that's why we say the universe was made in 3 minutes, because after 3 minutes, it means all the hydrogen, all the helium in the universe was manufactured. All of the fuel for all of the stars in the entire observable universe was made in 3 minutes. Now we go forward 380,000 years, mainly because the next 380,000 years are really boring, because nothing happens other than the universe continues to expand and continues to cool. But nothing much happens other than all the hydrogen atoms get all the hydrogen nuclei, the protons, get further apart, all of the 2 protons plus 2 neutrons, all of the helium nuclei get further apart as the universe expands. So the universe expands and cools, but nothing else of any interest happens. But there's a particular watershed at 380,000 years. What happens at that point? At that particular time, the universe has cooled to a particular temperature, about 3,000 Kelvin. Why is 3,000 Kelvin a particularly important temperature? Think about what's going on here on Earth. If objects are heated up to a few hundred degrees, they get hot and they start to glow. Heat them up to a few thousand degrees, they really start to get very hot and glow. What happens if you heat something up to 10,000 degrees? It completely vaporizes. The atoms fall apart. The electrons get stripped from their nuclei. Turn that around. In the early days of the universe was too hot for an atom to collect electrons for a nucleus to collect electrons to make atoms. But from this point onwards, now the universe is cooler than about 3,000 Kelvin, it is possible for nuclei to hang on to their electrons and actually make atoms. So this is the first point at which atoms, a nucleus plus a negatively charged electron, which up till now has just been floating around in the quark and electron soup of particles, nuclei can now hang on to their electrons and make atoms. So up to this point, the universe was simply an ionized plasma, lots of positive and negative charge floating around. But from this point onwards, it makes atoms. And when you make atoms, the universe turns transparent. Light can't travel through a plasma because it keeps rattling off all the negative and positive charge which is floating around. As soon as you make neutrally charged atoms, because every atom will have as much positive charge as negative charge, so they'll all be neutral, light can now travel through the universe unimpeded, because the universe, for the first time in its history, has turned transparent. So because it's transparent, light is released. Any light that up to this point was just rattling around in the plasma is now free to fly across the universe. And indeed, we see that light today. When the light was released, the universe was at 3,000 Kelvin, a brilliant white light. It would have produced a huge amount of visible light. But we don't see that visible light because the universe has continued expanding for the last 13.8 billion years. And so we see that light, but now it's been stretched out by the subsequent expansion of the universe. The universe is now 1,000 times bigger than it was back here. So the wavelength of light released at the time was, well, visible light, let's say it's about a micron in wavelength. But the universe is now 1,000 times bigger, so that wavelength is 1,000 times bigger. It's no longer a wavelength of about a micron, it's now a wavelength of about a millimeter. In other words, it's not visible light anymore, it's now microwaves. And that is the cosmic microwave background. The light released when the universe was 3,000 Kelvin, about 380,000 years old, because that's the point at which the universe turned transparent, and that's the point at which the, if you like, afterglow of the Big Bang was released to fly across the universe. And remember, we started this a long, long, long time ago by saying the universe was a lot smaller, the size of a golf ball, and the golf ball had dimples. There's the dimples. We see them in the cosmic microwave background. The cosmic microwave background, this is the whole sky, as it were, unwrapped and flattened out so we can see the whole sky. It's roughly the same temperature everywhere, in other words, the same intensity of light in all directions, except that there are a few splodges that are a bit hotter and a few splodges that are a bit colder. Hence a higher intensity of microwave or a lower intensity of microwave. Only small variations, less than 1 part in 1,000 variations, in other words, relatively small dimples. The small dimples in the golf ball have imprinted themselves in the cosmic microwave background. And that's one reason why it's very interesting to study the cosmic microwave background, because it's a handle to get an idea of what the very early universe actually looked like. So we have satellites, we have some ground-based experiments, but in addition we have satellites up there that are looking for these small variations in intensity, and we're trying to map them out as accurately as we can because it gives us such valuable information of what this early universe looked like. It's effectively as far back in time as we can possibly go. We can't look back any further than 380,000 years after the Big Bang, because before that time the universe was opaque. It was not transparent, so we can't see what was going on any further back than 380,000 years. So that the original cosmic microwave background is our earliest handle on looking at light from the early universe. So satellites are getting higher and higher precision, because the more we can understand about the cosmic microwave background, the greater our understanding of the Big Bang and the processes that led up to that particular point where the universe became transparent. We can get a good idea of what's happening by doing simulations. We can start, well, we don't start with a sphere, and we certainly don't start with one with dimples. What we say is, well, if we start with a chunk of the universe, let's just take not the entire universe, because computers can't deal with that. Let's take a small chunk of the universe, fill it with matter, and let's add some dimples, not physical dimples, let's add some small variations of density and temperature. So the blue here, the shade of blue, represents how dense the medium is. Perhaps you can tell that it looks a little bit mottled because some parts are just ever so slightly more dense or less dense than other bits. If we start with a whole load of matter with some variation of density, and then we let gravity do its stuff. We run a simulation that says if we understand how gravity works, if we start with a whole load of matter with a small variation in it, what will gravity do to that chunk of matter? We run the simulation for a few billion years, and what do we find? We find that dense parts get even denser, and less dense parts get even less dense. And the really dense parts are going white. Those are the most dense parts of this simulation. And notice that it doesn't occur uniformly. We get these white blobs, which are galaxies or galaxy clusters forming. We get them forming in filaments, and this filament makes a sort of web structure, hence we call this the cosmic web. And there are some regions which appear to be almost devoid. They appear to be almost black in this simulation, implying that there are very few galaxies in some parts of the universe and other parts of the universe which are absolutely chock of galaxies because there are whole clusters and superclusters. And this is the result of a simulation saying, let's start with what we think was going on in the very early universe. Let's put in a little bit of variation. Let gravity do its stuff. What do we end up with? We end up with a structure looks very similar to, remember the fly-through that I showed in the very second slide, where we know that the universe is not full uniformly of galaxies. It has galaxies in clusters, in strands, and we have other areas which occur in voids. In other words, very few galaxies. So the simulations of what if we start with something that looks like the cosmic microwave background and run a simulation forward for 13.8 billion years, the answer is we end up with a universe that looks very similar to the universe in which we are living. So maybe we've got most of our facts right. The Big Bang Theory certainly tells us about the cosmic microwave background. It tells us about the ratio of hydrogen to helium, and the universe that we end up with looks very similar to the universe in which we live. So that gives us confidence. Those three ideas, if you like, give us confidence that the Big Bang Theory is the correct explanation for how the universe came into existence and how it ends up looking the way it does. If we look at our immediate neighbor in a sort of a 3D map, there's the Milky Way and a few small satellite galaxies. We're surrounded by a few dozen. That's probably out of date. I think it's more likely to be a few hundred satellite galaxies around the Milky Way. This is our immediate neighborhood within a few million light years. So we've got the Andromeda galaxy down here, for instance, and we've got a few other relatively small galaxies dotted around the Triangulum galaxy as well. Of course, this doesn't tell us what the large-scale structure of the universe looks like because this is much too parochial. This is only our immediate neighborhood. If we go out to a slightly different scale, then we've got the local group of galaxies in this sort of region, and we look further out and we see some regions of our neighborhood are relatively sparse, and we see other clusters of galaxies like the Virgo cluster, and we're on the edge of the Virgo cluster, and there are other clusters like the Fornax cluster, etc. And perhaps you can already get the hint that these clusters are not randomly distributed throughout our neighborhood. They appear to be on a sort of a filament. There seems to be a line of them running top right to bottom left, and other regions which appear to be relatively empty. If we do the same again, let's change the scale to look a little bit further afield. Now the Virgo supercluster is right in the middle here. We're very close to that point there. And you can see that, again, there are strands, there are filaments. This is the cosmic web, again, mapped out in terms of where galaxies are. And we see huge regions of our neighborhood, our large-scale neighborhood, which appear to be almost completely void of any galaxies. And remember, this is all a consequence of the dimples in the golf ball, which eventually gave rise to variations in the cosmic microwave background, which, when gravity takes hold, eventually pulls stuff together to make galaxies in some regions, and it leaves other areas devoid of galaxies. So we know these voids exist, we know these filaments exist, we know galaxies are spread throughout the universe in a way which is not uniform and not totally random, but has a particular structure, and we can understand that structure by running simulations of how gravity gets hold of these variations in density from the very early universe. The next 13.8 billion years, you could say, well, we've pretty much got it sussed. If we understand that it only takes 3 minutes to make all the hydrogen, and we know that stars are just basically factories for taking the hydrogen and making other elements, including, of course, not just helium, but carbon, nitrogen, oxygen, calcium, phosphorus, iron, all of the elements that make us, basically. We know that that's what stars are doing. All they need to start with is enough hydrogen, and all that hydrogen existed after the first 3 minutes. If we understand where the hydrogen comes from, then you could say, rather arrogantly, well, in that case, we understand everything. We understand galaxies, and we understand stars, and we understand planets, and trees, and mountains, and snowflakes, and rainbows, and cats, and okay, not cats. I don't think anybody understands cats, but I mean, we understand everything else. If we understand hydrogen, we can say rather naively, well, yeah, then everything else flows from that, because we understand that stars start with hydrogen and make all the heavier elements, and we know that heavier elements form planets like the Earth, etc. So we know pretty much everything. Well, okay, not quite everything. There are still some details to be worked out, which is why we still have telescopes and space telescopes and everything else. There are some things to be worked out, but you could argue on the grandest scale of things, if the Big Bang theory is correct, then we understand where the hydrogen comes from, and therefore we understand everything about stellar evolution and planetary evolution thereafter. So just to summarize on a very silly timeline, from very low, very small times on the left to very long times on the right. So there's the cosmic golf ball on the left-hand side, and there's us now 13.8 billion years later. So we borrow energy from nothing. We generate a quark soup, because if we borrow energy, we can make matter and antimatter. So we have a whole load of quarks and antiquarks and electrons and anti-electrons and a whole load of other stuff in there, very exotic particles which probably don't live very long. That doesn't matter. We've got lots of quarks and lots of electrons because we've borrowed energy from nothing, and we're allowed to do that. After a certain length of time, after a few seconds, some of those quarks, because the temperature has now dropped enough, some of those quarks to get together to make protons and neutrons. After a few minutes, the protons and neutrons can get together, but they don't all make helium, because protons and neutrons are not made in the same numbers. Protons are lighter, so there's more of them, so we end up with much more hydrogen than we end up with helium. 3/4 to 1/4 is the ratio predicted. After 380,000 years, eventually the electrons come back into the picture. Nuclei can hang on to electrons because the universe is now cool enough to do that. And as soon as the universe turns transparent, the light is released, and the light we see is the cosmic microwave background. 1,000 times bigger wavelength, because the universe has expanded 1,000-fold since the light was released. There's still a little bit of a period after the cosmic microwave background was released, which we call the Dark Ages. Once the cosmic microwave background light existed, how long did it take until the first stars took that hydrogen, allowed that hydrogen cloud to collapse, and started making the first stars? That is something we don't actually know. How long were the Dark Ages between 380,000 years and when the first stars and the first galaxies were born? That is why the James Webb Space Telescope is up there, looking as far back in time as it can to try and work out, were the first stars and the first galaxies born 500 million years after the Big Bang, or 400 million years, or 300 or 200 or less? At the moment, it seems to be rather surprising that the Dark Ages were rather shorter than we first thought. Many people assumed the Dark Ages would last for 500 million years or 1 billion years before the first stars came along. But now it looks like those first stars were there very, very early. We don't know exactly when, because James Webb Space Telescope hasn't finished its mission yet. It's still pushing the boundary back to earlier and earlier times. And now, of course, we know what the universe looks like in terms of local galaxies, in terms of galaxy structure, and we can see back in time to see what those early galaxies look like as well. So we've got a pretty good idea of galaxy evolution. But yes, I said that was a rather arrogant assumption to assume that if we know where all the hydrogen comes from, then we know everything. That's clearly not the case. We've got most of the pieces of the jigsaw sorted, but there's still a few gaps that we need to figure out. The really important questions which we haven't yet answered is, this is all predicated on the fact that for some reason energy did not make equal amounts of matter and antimatter at some point in the very early universe. Antimatter took a back seat and matter gained an excess, only 1 part in a billion, but it wasn't zero. It was a finite excess. What is it that caused the asymmetry to give us more matter than antimatter, such that when all the matter and antimatter are annihilated to make all of the light, what we're left with is matter, which is, as far as we can tell, pretty much everything in the observable universe. And I haven't been talking about dark matter. I've been trying to be very careful to talk about everything that we can see. When we look out into the universe and we see all of the gas and the dust and the stars and the galaxies, I'm talking about where all of that came from. I haven't even mentioned dark matter. We don't know what it is. We think it's out there. Presumably it was born in the Big Bang, but we have no solid evidence because we don't know what dark matter is. We think it's out there because, for instance, galaxies are rotating at speeds which we wouldn't otherwise expect, looking at what's actually out there. And don't get me started on dark energy. The universe is expanding, and it would appear that compared to when I was a nipper, when the expansion of the universe was probably slowing down, oh dear, it isn't. We now realize from observations of the last few decades that the expansion of the universe, far from slowing down, is actually accelerating. And we don't know why, but we've given it the name. The cause is dark energy. That means absolutely nothing because we don't know what it is or why it's there. But that is what we are using as the label for the thing that is causing the acceleration of the expansion of the universe. So yes, this talk is called The Beginning of Everything, but by everything, I mean everything that we can see, everything that's luminous, all the stars, all the galaxies, all the gas, all the dust that we can see by one means or another, but that actually only accounts for 5% of the universe. The other 95%, dark matter, dark energy, is still, to this day, a bit of a mystery. But as they say, that's another story. Thank you.